Hello! In this video, I would like to talk about some selected subfields of the complex number field. Let's dive in. We will start indeed with the field of rational numbers. Including the number 1, field operations will generate all rational numbers. Hence, every subfield of the complex number field contains the field of rational numbers. It follows that rational numbers, and for that matter real numbers, have only one field automorphism. This is not the case of the complex number field, which has many. Of course, we all know that rational numbers can be expressed in a form of fraction. More exciting, however, is the use of continued fractions. Now, for a rational number, the continued fraction is finite, albeit not unique. Its coefficients can be obtained by running the Euclidean algorithm on the numerator and the denominator, and it is obvious that this process must be finite. Now, let us start with an infinite continued fraction. The simplest infinite continued fraction has all coefficients equal to 1. How do we evaluate it as F-decimal? We construct the sequence of rational numbers by truncating the tails. Doing this for the simplest continued fraction made of only ones produces a sequence of fractions, with denominators being exactly the members of the famous Fibonacci sequence, and the corresponding numerators being the numbers that follow the denominators in the very same sequence. The limit of the sequence is an irrational number, phi, or 1 plus the square root of 5 divided by 2, known as the golden ratio. You have been looking the whole time at the red rectangle representing the rational numbers. The ratio of its sides is exactly phi. It has been said that such a rectangle, among all rectangles, is the most pleasing to look at. The golden spiral and the Fibonacci sequence was observed in an arrangement of leaves and petals of certain plants, so perhaps it is not just saying. Phi is not only known as an irrational number, it is also known as a constructible number. This is in a sense that if we start with a line segment of a unit length, using only a straight edge and a compass, we can construct a line segment of a 1 plus the square root of 5 over 2 length. Another example of a constructible irrational number is the square root of 2. Indeed, starting with a line segment of a unit length, we can use a compass to draw a unit circle. If we manage to find a line perpendicular to the original line segment, we can form a triangle with the hypotenuse of a square root of 2 length. Such a perpendicular line is constructible with two larger circles, here depicted dashed. All constructible numbers form a field, the smallest ordered field containing rational numbers for which every non-negative element is a square of some other element from this field. We call such fields Euclidean, so we can say that the field of constructible numbers form the Euclidean closure of the field of rational numbers. Moving on to non-constructible numbers, the third root of 2 is a prime example. When the oracle at Delphi asked for an altar to be doubled, it unwittingly started a 2 millennia long quest for constructing a cube with a side of such a length by means of only a straight edge and a compass. It was only when algebra and geometry were joined by Descartes' coordinate system that it was possible to prove this task undoable. Nevertheless, the third root of 2 is a solution to a polynomial with rational coefficients. If we add all such real roots to the field of rational numbers, we obtain again a field. It is a field of all real algebraic numbers, the largest algebraic extension of rational numbers that still permits ordering. The absolutely largest algebraic extension of rational numbers is the field of all complex algebraic numbers. You have all perhaps seen a joke with I and E calling each other out, be rational, and get real respectively. Here is my version of the joke. I, a solution to x squared equals -1, is proud to be algebraic. Look E, I'm algebraic, it calls. Just to be reminded by non-algebraic E, listen I, you are not real. Imaginary numbers such as I are not just possible roots of polynomials with rational coefficients, but they are also helpful tools in finding real roots. Here is an example of a polynomial with rational coefficients. It has 3 real roots, 3 real algebraic numbers, 1 plus the square root of 3, -2, and 1 minus the square root of 3. Nevertheless, in order to obtain them using forgotten Cardano's formula, discovered actually by Del Ferro and Tartaglia, and conveyed to Cardano in a poem, we must work with imaginary numbers. Imaginary friends that help us in the real world. Would you call that crazy? Of course, there is nothing crazy about imaginary numbers. Other than that the square root of -1 times -1 is not the square root of -1 times the square root of -1. That is what I call crazy. Whether we look only at real algebraic numbers or also at complex algebraic numbers, we discover that algebraic numbers are unbelievably rare among all real numbers. Why is it so? First, we can obviously transform all polynomials with rational coefficients to their equivalent polynomials with integer coefficients. Second, we define an invariant, capital N, with only a finite number of polynomials having it. Since countable union of finite sets is countable, there is only countably many polynomials. Similarly, each polynomial has only finitely many solutions, so countable union of finite sets of roots makes a countably infinite set of all polynomial roots. However, there are so many real numbers that we cannot even arrange them into a sequence. They are not countable. If we assume this possible, we would be always able to construct an element by Cantor's diagonalization that does not belong to the original sequence. The field of all real numbers is uncountably infinite. Strangely, there are as many complex numbers as there are real numbers. An argument can be made using Hilbert's continuous space-filling curve. Infinities are strange indeed. In fact, this field of real numbers is so big and peculiar that every non-zero element in this field has a twin called a Liouville number. We construct these twins by spreading the digits of the original numbers by increasingly larger number of zeros. These Liouville numbers are transcendental. That means they are not algebraic. They are not solutions to any polynomial with rational coefficients. Since there are as many of them as real numbers, they are uncountable, and they all have their Liouville twins themselves. How peculiar! Moving on to a more typical examples of transcendental numbers, we arrive to e and pi. Behold, e reminding I that it is not real. Who will win this bragging competition, e or I? Let me know in the comments. While E is called Euler's number, what was voted to be the most beautiful identity in mathematics, e to the I pi equals -1, is actually due to Cotes. Euler had an identity concerning pi, which was in its time equally famous. It is quite fascinating that E has a well-behaved continued fraction with a pattern, but there is none known for pi. Continued fractions, along with Cauchy sequences and the Dedekind cuts, can be viewed as a tool to construct the field of real numbers. And in so many ways, continued fractions are their more natural representation. Just ponder it for a moment. Rational numbers have finite continued fractions, while irrational numbers have infinite continued fractions. And when we truncate these infinite continued fractions, we obtain the best rational approximation of these irrational numbers. For example, truncating the continued fraction for pi gives us a sequence of 3, 22/7, 333/106, 355/113, and so on, all of them being famous approximations of pi. Famous in a sense that they do better than we would normally expect for such small denominators. Finally, arriving to the field of complex numbers itself, it can be defined as the smallest algebraically closed field containing the real numbers, or as the largest algebraic extension of real numbers. We have already mentioned that the largest algebraic extension of rational numbers is the field of complex algebraic numbers. We can now also say that it is the smallest algebraically closed field containing rational numbers. The meaning of algebraic closure is that all polynomials with coefficients in the field have all their roots defined in the field. How neat! And here you have it, selected subfields of the complex number field in one math chart. Best wishes from Math Charts!